In this section, we're going to cover the concept of probability. Now, probability is the best and also the worst, only because it's going to take everything we've learned in the previous sections, and now we're just going to tack on top of that. So, first thing I want to do is make sure I talk about the definition of probability with you. And then we're going to do a couple other things. We're going to talk about probability distribution tables and the addition principle of probability. Now, that being said, the main, if you can walk away with definition of probability today and how to write probability distribution tables, that's my biggest concern today. Now, here we go. The good news. If I asked you, what is the probability of flipping heads when flipping a fair coin? Most of you probably already know how to do this. Now, when I say fair, maybe the only thing that you might be questioning. When I say fair, that just means it has the likelihood of either side coming up is the same. It's not a weighted coin. It's not going to flip heads every single time. So it means it's going to come up tails half the time, and it's going to come up heads half the time. So if I want you to try, just pause this video and get an idea of what you think the probability of flipping heads, just using your own knowledge, what you already walk into this class with. Okay, what'd you come up with? Yeah, tell it to me. Okay, don't. So I'm hoping you have one of these different kinds of representations. You may have said 1/2, or you might have said 50-50, or you might have said 50%, okay, or 1-to-1. Now, I will tell you, not all of these are actually probabilities. This one here, this one here is actually the 1-to-1 is actually odds, not probability. There is a difference between the two, and we can cover that later in the class. But for right now, and same thing with the 50-50, that is odds. That is not probability. Okay. But the 1/2, 50%, or you could write it as 1-to-2, that would be probability. And the idea here for probability, the definition of probability, is quite simple. It's a comparison between the, and I'll phrase it as desired outcome, desired, over the total number of possibilities. Well, isn't that kind of just the same idea as the cardinality of the event divided by the cardinality of the sample space, right? Just what is the total number of possibilities, and then what is the total number of ones that would make me win the game? That's probability. So if I'm talking about flipping a heads, then what I'm saying is there's one way on a coin for me to flip a heads, because it either has heads or it has tails. So there is one, and if I say I'm going to win the game by flipping heads, there's one outcome that will make me win the game out of a total of 2 possible outcomes. Now, going forward, we're not going to say that coins are fair. We're just going to assume that they are. And if a problem doesn't want them to be fair, it'll need to state so. Same thing with dice, same thing with any kind of random odd object. We're going to assume it's fair unless otherwise stated. Okay? So, what is the definition of probability? Well, for this class, I really want you to think of it as counting the number of events, the cardinality of the events, and dividing that by the cardinality of the sample space. That is our definition of probability. So, that's it. So you kind of already knew that. It's just going to be different representations, right? We're going to go into different representations, harder problems. And so what's another representation of writing 1 divided by 2? Well, that would be 0.5, right? We could write as 0.5 or 0.5. Or if you want to change that as a percentage, you could write that as 50%. And so the question, at least for my standards, is which of these representations is correct? And my answer is all of them. Unless the problem specifically states it wants it represented as a fraction or a decimal as a percentage, all of them are fair representations as long as they are exact. So for example, if you run into a problem where the probability is 1 out of 3, okay, you cannot then tell me 0.3 is your answer. No, that's not exact. 0.33 is not exact. 0.333 is not exact, right? You get the game. And I'm really not a fan of putting a little bar over the last digit of the 3 to show that it's repeating forever. No, just write as 1/3. We're past that. We're at the point where we can write fractions, right? Right? Okay. Now, if it specifically says to write it as a percentage, then you're going to be forced to write 33.3%, and you'll have to use that repeating bar because they forced you into that representation. But if you're not forced, if they give you the option, fractions are the way to go. Okay? Especially if in the scenario where it is a repeating decimal or something of that nature. Okay. So that's the basics of probability. Now let's get the basics of a probability distribution table. Now, a probability distribution table is a simple idea. It lists all of the possible events and the probability for each of those events. So what that means is, let's say we had 3 different events, maybe A, B, and C. Don't fill this in because we're going to fill in something else in the notes. I'm going to erase this. A, B, and C. Then the probability of A happening maybe is 1 out of 4. The probability of B happening is maybe 1 out of 4. The probability of C happening is 2 out of 4. Now, if I've listed every possible event, that means there's nothing else that could occur, right? It's either A, B, or C. There is no D, otherwise it would have to be listed in my table. And also, therefore, the probabilities have to add up to make 1, or 4 out of 4, or 100%, right? Meaning either A will happen, B will happen, or C will happen 100% of the time. So when you're looking at a probability distribution table, and maybe it looked like this, it had 1/4, 1/4, 1/4. Well, then you would look at it and say there's something wrong because this does not represent all of my possible outcomes, because right now I only have 3/4 of my outcomes represented. So the key to a probability distribution table is your probabilities have to add up to make 1, and it must list every single possible outcome, every single possible event. So let's make a probability distribution table for flipping 1 coin. Well, what are my possible outcomes? I could either flip a heads or I could flip a tails. Now, the probability of that happening would be, well, I could get a heads 1/2 of the time, or I could get a tails 1/2 of the time. Therefore, this probability distribution table is perfect. It works, right? Okay, that's it. So that's how we do probability distribution tables. Now, they're going to seem kind of weird. We're going to learn how to do them here. We're going to play and fill them out a lot, and then they're going to kind of go away for a little bit. They'll come back when we get to a concept of expected values. When we get to expected values, you're going to need these. So when you get to a lesson that starts mentioning those, if you don't remember these, maybe come back and review them real fast. Okay. So now we're just into practice because kind of that's the whole lesson. So now we're just going to do a couple practice problems. So what is the probability of rolling a sum of 3 when rolling 2 distinguishable dice? Okay. So how do we figure out probabilities? It's the definition of the cardinality of the event divided by the cardinality of the sample space. So when I'm rolling 2 distinguishable dice, you choose. These are 2 separate problems, and it's your choice how you want to do them. We can either do the numerator first or the denominator first, but they're totally separate. I'll start with the denominator because it's usually easier. Not always, but usually. So when I'm rolling 2 distinguishable dice, I don't need to worry about the sum of 3 because I'm doing the sample space. Just how many different outcomes are there? Well, if I'm rolling 2 dice, that means for my first die, I have a decision. I have to decide what is going to come up on that dice, and I have 6 choices. Then for my second die, again, I have 6 choices. So therefore, die 1, die 2, 6 times 6 makes 36. I have a total of 36 choices. All right. So then for the numerator, similarly, how many different ways are there for me to roll a sum of 3? Now, stuff like this, I highly recommend just start making a list, make a pattern. Don't try and do it counting when it's such a small set. You say, okay, I have 2 distinguishable dice, maybe a red die and a blue die. On the red die, I can roll a 1, and if I roll a 1, then my blue die has to roll a 2. On my red die, if I roll a 2, then my blue die has to roll a 1. There's no other ways for me to get a sum of 3 because there's no way for me to roll a 0 on a die. That can't happen, right? They're 1 through 6. So therefore, what's the cardinality of the event? There are 2 possible ways. So therefore, the probability is 2 out of 36 or 1 out of 18. And there you go. Now, my favorite question ever. Take a second. What is the probability of rolling a sum of 3 when rolling two indistinguishable dice? I'm going to let you think of that one for a minute. Maybe you want to pause the video and give it a try. Or not. Here we go. The answer is 1 out of 18. I'm not doing any work. Why am I doing any work? Because it's common sense. All right, and this is why I say it's common sense. Think about it this way. You walk up to one table in Las Vegas, you walk up to another table in Las Vegas, and they say to you, this one has distinguishable dice, so you can tell this one has a red die and a blue die. This table has indistinguishable dice. You can't tell the difference between them. They're just both white. And someone says to you, you're going to win the game if you roll a sum of a 3. So you're going to roll the 2 dice. You're going to get a sum of 3. Which table do you want to play on? Are you really going to make the argument that the color of the die matters? That because these die are white, you're going to win less often? No, that's silly. That's ridiculous. So in probability, there is indistinguishable does not matter, right? Everything is distinguishable. Imagine the white die, one of them has a little dot in it somewhere where you can tell the difference. So now they become distinguishable, right? So it's the same problem. Indistinguishable is garbage in probability in this context. Does not matter. Distinguishable dice, indistinguishable dice. You just pretend you are some higher power. You can tell the difference. Everything is distinguishable. So the answer is 1/18 for the exact same reason as the problem above. Okay. So now let's make a probability distribution table describing the sum of 2 indistinguishable dice. All right. So here we go. What are the events and what is the probability of said event? Here we go. All right, so if we're doing the sum of the 2 dice, the sum, what is that? What are my possible outcomes? I have to list all of them. Well, what's the lowest I could ever get? Well, I could get a 1 and a 1, which make 2. Then I could get a 3 and a 4 and a 5, right? Just by getting different amounts on the die. Now, so this will continue on. I'm not going to do a dot, dot, dot. I just got to know where to stop. If each die goes up as high as having 6 on a side, then that means the highest number I can ever reach is 12. So every other possible sum in between is possible though, right? So 9, 10, 11, 12. There we go. Didn't need to go that far over. Alrighty. So those are every single possible outcome. Now let's do the probability for each of them. Well, we already did the probability for rolling a 3. I'm going to leave it as 2 out of 36. Just because I want to have common denominators. So if I don't simplify my fractions, it's going to make my denominators be all the same. Because the total number of outcomes, regardless of if I'm trying to roll a 5 to win a game or a 6 to win a game, whatever I'm trying to win, the total number of outcomes is going to be 36 when I'm rolling 2 die and adding the faces together, right? 36 possible outcomes. So how many ways are there for me to roll a 2? Well, there's only one way to do that, right? I have to roll a 1 and a 1. And it doesn't matter the order in which I roll them because order isn't important. What we're talking about is red die, blue die, right? They're distinguishable. So if I switch the quote-unquote order, it's still the red die rolling, excuse me, the red die rolling a 1 and the blue die rolling a 1. It's still 1. These are the same scenario. So there we go. All right, how many ways are there for me to roll a 4? Well, all right, let's see. I'm going to go over here to the side. To roll a 4, I could roll a 1 and a 3, a 2 and a 2, a 3 and a 1. And that's it, because you can't roll zeros. So therefore, there are a total of 3 ways. Noticing a pattern, anybody? So pause the video, try to fill this in. And if you're not, just go through and make the whole list, okay? All right, so I'm going to go ahead and fill this in now. So it is 4, 5, 6, 5, 5, 4, 3, 2, 1. Right, so there are these are the probabilities of rolling all your different values, and you'll notice 7 has the highest amount. And if you didn't figure out why, let me point it out really fast. 7 is created by rolling the lowest amount on one die and the highest amount on the other die, which means that no matter what I roll on my first die, whether it be a 1, a 2, a 3, a 4, a 5, a 6, or 6, there's always an option in the other die to create a 7. So if I roll a 2, I can still roll a 5. If I roll a 4, I can still roll a 3, right? There's always a pairing, where every other die does not have that ability. So for example, if I roll a 1 on my red die, and I say, okay, what do I need to roll to get an 8? Well, you'd say that's impossible, because I would have to roll a 7 and it only goes up to 6, right? So, and that's true for any other number other than 7. 7 is the only one that has that quality. Okay, so there's our probability distribution table. Let's verify that we got all of our options. If we add these up, this is why I want common denominators. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1. That equals, pause the video if you need to do it, that equals 36 out of 36, which means we got them all. Yay, we're amazing. Okay, so that pretty much finishes off the big ideas from this section. So everything going forward will be review and just practice problems. All right, we'll see you in the next video.